Okay.
So by 12:45.
Good morning to all. So to begin with, I am thankful to Professor Javed Ali and his team for inviting me for this GAL program. So I will speak on this topic: two basic topo-analytic hybrid-Fishburne theorems and nonlinear differential equation. So I hope all of you are aware of the fact that most of the dynamic systems, they are not linear. Straightforward. Complicated means they are non-linear in nature. So first, French mathematicians Henry Poincaré first recognized the importance of such type of equation, nonlinear equations, and he predicted that future mathematics would deal with only nonlinear equations. So this is very difficult to deal with nonlinear equations. Even if there is a simple nonlinear equation, it is not possible to solve it. So different approaches by different mathematicians have developed. So one is say there are different differential inequality. Another one approximation theory, approximation method. Third one is that numerical methods. Fourth one say function analysis method, and so on. Different approaches are there. So nonlinear operator theory from the subject of nonlinear function analysis provide very powerful tools for the analysis of such nonlinear problems. And so this is nonlinear analysis. So study of such type of equations for different qualitative analysis is the nonlinear analysis. It is subject of nonlinear analysis. So we discuss here function analytic methods, even though my interest in other approaches also. But these nonlinear operator theory from nonlinear function analysis provide powerful tools for the analysis of such type of problems, nonlinear problems. So one fixed point theory is one of the part of that operator theory. So it's a big area. Operator theory is a big area. So fixed point theory is one part of that operator theory. And I think so fixed point theory and differential equation, of course nonlinear differential equation, theory of nonlinear differential equation. These two fields are not say what you can say different. The development of these two topics they goes hand to hand, because origin of fixed point theory lies in the differential equation, and the development of multitude development of differential equation is because of fixed point theory. It is correlated. These two fields are closely related to each other. So so this fixed point differential equation is the motivation for the fixed point theory. Remember, even though there are so many fixed point theories, people are proving some generalization extension, because differential theory of differential equation is the motivation for the development of fixed point theory. Fixed point theory. Remember, so I know that all of you are interested in the application of fixed point theory, fixed point theorems to differential equations. Yesterday I discussed this problem with so many participants. They are interested how to apply and how to apply, where to apply fixed point theorems to differential equations. Of course, it is not difficult at all. It requires a little skill and some computation, a little skill, and selection of proper fixed point theorem. Remember, clever selection of fixed point theorem gives you cleverer results, good results you will give. But you have to select the exact or nice fixed point theorem, depending on the situation. Depending on the situation. So it's not working, no? So I start with very simple problem. So first, this linear first order differential equation. I start with this simple problem. Say given a closed and bounded interval J in R for some T0 A belongs to R with A is greater than 0. We consider the linear simple differential equation x dash of t, this x of t belongs to J. This is the with initial subject to some initial condition like this. Real. It is a simple one, simple linear differential equation. You can solve it by We have methods how to solve it. For separation of variable and so on. This one. We can solve this, no problem. So now, what I do see like this. I just perturb or modify or replace this linearity, the unknown function, this unknown function, which value is to be calculated. So I replace this by nonlinear function, like this. X dash of t is equal to this is nonlinear function, and with same subject to some initial condition like this. I don't put any condition on this function so far. It's a function from J cross R cross. It's real. It's a real differential equation, not abstract. So I do not put presently any condition on this nonlinearity. So if it is a nonlinearity, we say it is nonlinearity because it is not linear in x, unknown variable. If it is linear in x, no problem. No. So it is not linear means it is nonlinear in x. So we say it is nonlinear function, nonlinearity. So this nonlinearity involved in this differential equation. This is the most famous differential equation. First, the fundamental equation of the nonlinear analysis. Fundamental equation in nonlinear analysis. So it is a rich source of the investigation of development of nonlinear analysis. Everything starts from here. So what is there are several methods. I told you there are several methods. So one is this operator theory method for fixed point theory. So first, who tried Picard iteration method? He is the first person to deal with such a problem. So what Picard did, what he did just he assumed that F is continuous, and he considered one Lipschitz condition. This is a Lipschitz condition. He considered, so this satisfies a Lipschitz condition. So his assumption was like this. So this assumption where F is continuous and F satisfies the Lipschitz condition, and here again more he assumed it is bounded. Then this problem has a solution, unique solution. I mean, it has a solution provided this Lipschitz constant satisfies this condition. L A is less than 1. So if this Lipschitz constant, this Lipschitz condition, famous Lipschitz condition. So if this Lipschitz constant satisfies this condition, L means this interval, this. If L is less than 1, F is continuous and satisfies Lipschitz condition with this condition, one more condition, then he proved that this problem, this nonlinear differential equation, has a solution, and the sequence of successive approximation defined by like this. You know this. It converges to x star. This sequence goes to x star. X star is a unique solution of this differential equation. This is the famous Picard iteration method. So its proof is lengthy, quite lengthy, 2-3 pages, and involves many more analysis. So then what the Banach did? Remember, Banach it is not his own theorem. He borrowed the idea from this Picard. He just extended the idea of Picard to abstract setting in the metric space. That's all. Same with same proof, same method, everything is same. But it has become more popular. The Banach quantization mapping principle. Basic idea is of Picard. He just extended that idea to metric spaces. What is the advantage? So advantage is that in if you apply Banach quantization mapping principle, within 2-3 steps you will get the solution, unique solution, and the same conclusion. Sequence of successive approximation goes to the solution, that unique solution. 2-3 steps. This is the advantage of that. One more advantage is there. So in Picard iteration method, it is assumed that L is less than 1. Then it becomes quantization. But if you apply Banach quantization principle, there is no need. For any Lipschitz condition, it works. I have one paper proved in this. Lipschitz condition. It is proved in Indian Journal of Pure and Applied Maths in 1997. So in that paper, this condition is relaxed. It is redundant. I have applied Banach quantum principle, but no condition on the Lipschitz constant. How it is done? The actually renorming of the space. I have renormed that space, equivalent norm. Another norm is defined, which is equivalent to previous norm, and then shown it is a Banach contraction. And without making any assumption on this Lipschitz constant, we get the unique solution. So this is the advantage of Banach contraction mapping principle. How it is done now? How Banach contraction principle is applied? Very simple. So 2-3 steps. Very simple. How to apply Banach contraction principle to differential equation, nonlinear differential equation. So first of all, it requires a little skill. Remember, problem is given, okay? Differential equation is given. You first of all find what about its solution. You have to write the definition of the solution, where it belongs, where the solution belongs to which function space. You try to find the function space, appropriate function space, and then you place this problem into that function space. So generally here we assume continuous. So space of continuous and bounded continuous function, real value continuous function on J, closed interval J, CGR. Here we have placed this problem into this place. This is the proper space. So you first of all you place your problem into a particular space, abstract space. Then we can apply. So metric space is not a linear space. It is non-linear space. So metric space cannot be considered for application at all. So you have to always consider a linear space for the application. So we consider this linear space. It is Banach space with supremum norm, and it is Banach space. So this function is taken for the study, appropriate function space, and you place this problem into this space, and this norm generates a metric. So it is compared with respect to that metric. So it becomes a Banach space. So this is first step of application. What is the first step of application? You find a appropriate function space for the solution, and you place that problem in that function space. Okay. So then second step is very simple. Function is continuous. It is integrable. Function is continuous. Therefore, it is so we consider only Riemann integration, not Lebesgue or any other integration. Only so it is integrable, Riemann integrable. Okay. Then you just integrate both sides using the theory of calculus. You apply the fundamental theorem of calculus. What is the fundamental theorem? You know, might be knowing all of you. What is the fundamental theorem of calculus? So we apply fundamental theorem of calculus on this. So what do you get here? Like this. Here, this side you apply. It exists because function is continuous. Therefore, it is integrable. So this integral exists. The second step. This is the second step. You convert, and what is the left hand side? Just you will get here like this. This is the second step. You make use of calculus, using the theory of calculus, using the fundamental theorem of calculus, you convert the given problem, given differential equation, nonlinear differential equation into an equivalent integral equation. This is also nonlinear. So it is equivalent integral equation. This is the second step. Once this is your established now, the rest of things are very easy. Two things remember: given problem is there, find the appropriate function space, then find the corresponding integral equation, equivalent integral equation. Okay. Now next step. Now you convert this integral equation into operator equation. Simple. Just you put the right hand side of this is operator T of x of t. Then this equation is converted into what? Operator equation like this. So this is operator equation. You consider right hand side to be an operator, T, some operator, so that this equation can be transformed into this operator equation. And solution of this operator equation is the solution of the, because it is equivalent. Since this operator equation is equivalent to this equation, so the solution of that is the solution of this, and solution of this is solution of finish. It is like this. Simple, very simple. How to apply? So then you have to show that this operator equation in the space CGR. This is Banach space. Just to show that it is a contraction. If you want to apply Banach contraction principle, just to show, take 2 points. Only 2 points, you consider 2 points like this. Then find this. Find this. So what you can, this equal to what? Mod here, this get cancelled, x0, equivalent integral equation. So you like this. I need not work out the details. It is well known. Because of Lipschitz condition, what to get here? This is equal to, because of Lipschitz condition, you get here total. I write here L A, because it is Lipschitz. Because of Lipschitz condition, we get this relation. And taking the supremum again, what we get here? Over T, take the supremum over T. T over belongs to T over J. So we get this contraction. So it is Banach contraction. So apply Banach contraction principle, very simple. So convert into integral equation, right hand side is the operator, convert into transform to operator equation, apply Banach contraction principle. This contraction, space is complete, it has unique fixed point. And that unique fixed point is the solution of this operator equation. What is the solution? What is the fixed point? Fixed point is the invariant point under this transformation, right? So this is the fixed point. So solution means fixed point. So fixed point means solution of this operator equation. And that solution of this operator equation is correspond what it is to the integral equation. And the solution of integral equation is the solution of differential equation. Finish. So simple. How to apply fixed point theorem to? But remember here, it requires a little skill, because depending on the circumstances, differential equation is given. What is the nature of this nonlinear function? You have to first think over it. What is the nature of this nonlinear function? So if it is continuous, say bounded satisfied Lipschitz condition, then you can apply. Otherwise, you cannot apply. Otherwise, you cannot apply. So again, this theorem fails. Banach contraction maximum fails somewhere. There are certain situations, certain differential equation. So this is not this theorem doesn't work. Banach contraction principle doesn't work. So I have improved that this Banach contraction principle. So some here linear contraction is there. So I just here it is okay. It works. Analytic. This is right. So I consider this one more definition, two definition. So D function, I introduce a one D function, which is upper semi-continuous, non-decreasing, and that satisfies psi of 0 equal to. So it is a D function. Making use of this D function, I consider this nonlinear contraction. D Lipschitz, this Lipschitz, definition of D Lipschitz, and if psi of r is less than 1, this is nonlinear D contraction. So it is special of this is contraction. Special of this nonlinear D contraction is this contraction. So there are situations in differential equation where we do not use this Banach contraction principle, but this is useful. These differences. Theorem is same. Same is if a function t from a complete matrix space into X itself is nonlinear D contraction, then it has a unique fixed point x star, and a sequence of successive iteration goes to the unique fixed point x star. The conclusion is same, but this is slightly improved. That condition is slightly improved. So one paper is a Cubo journal. I approve one theorem. One paper with Grabe, and so on. How this is a paper. In that paper, we utilize this particular fixed point theorem. This theorem we have utilized here. So here Banach contraction doesn't work. So this is advantage of this particular theorem. So now see here, what are the conditions? Suppose F doesn't satisfy Lipschitz condition. It is continuous. It is continuous, and then it is bounded. If boundedness is required only for local solution, not for any other solution. If you do not use bounded condition on the function of no, they will get a solution, but not in local solution. So if there is function is continuous and F is also bounded, Then another theorem, another fixed point theorem proved by J. Schroeder. It can be applied. Topological fixed point theorem. So all the fixed point theorem on the line of Banach quantization principle is analytical fixed point theory. This is the analytical fixed point theory. That is metric fixed point theory, you may say. Metric fixed point theory. So in mid-France, yeah.
Sir, can you tell about this paper?
Which one? Cubo that published. You can search in Google and.
No, he's asking, say something more about this paper.
Yes.
Because it is used in fractional calculus also. So I am interested in this topic also.
Fractional,
Fractional calculus.
we are going away from the topic. We shall discuss it because I am just, so actually in 1 hour, it is not possible even we touch to our topic. That hybrid, we can't go. Only just I am explaining the just fundamental application of fixed point theorems or fundamental theorems. So there are very few fixed point theorems in analytic theory, very few, like Banach quantization, such generalization, and other fixed point theorems, they don't have any application. Even famous Cannon fixed point theorem proved in, I think, 1965, 67 something, it has no application. And afterward, there is no application at all. Only for the sake of entertainment. It's all right. Sometime in future, it may have application. I don't claim that none has application. In future, those may have application. But so far, it is not application. So only few fixed point theorems in analytic theory have applications. So next, let me go to the, if change the situation. This doesn't satisfy Lipschitz condition. Then does this problem have a solution? Problem. It doesn't satisfy Lipschitz condition. Lipschitz condition is a very strong condition. In nonlinear analysis, this condition is supposed to be very strong. We generally never assume this condition. It's very strong condition. And you know how it is satisfied. If this is less than or equal to some constant, it satisfies this condition, Lipschitz condition. That is, all right. But this is very strong condition. Next, if the function doesn't satisfy this condition, it is continuous and bounded, what happens? Does it have a solution? In that case, the J. Schroeder, Polish mathematician J. Schroeder, he proved one theorem in the infinite dimensional space, named after Schroeder fixed point theorem. So that theorem is useful here in this case. Same procedure. So this same procedure, this is the same procedure. So you have to consider what is that theorem? Theorem is like this. This is topological fixed point theory. So after Schroeder, the first version of this Schroeder fixed point theorem lies in the Brouwer fixed point theorem, which is in final dimensional Banach space. Final dimensional space. This is infinite dimensional Banach space. So he proved that a continuous operator T or a complex convex subset of a S of a Banach space has a fixed point. Simple, very simple. But this theorem is not applicable because it is very difficult to find a complex subset of Banach space. Always, it's not possible. So then this theorem is applicable. It's a modification of this theorem. One and the same, little modification. So yes, we are non-closed continuous and bounded subset of Banach space, and let this is the completely continuous operator. So completely continuous operator means this one. Then it has a fixed point. So this is the famous Schroeder fixed point theorem. Can be applied without Lipschitz condition, only under the assumptions of this continuity and compactness condition. Here in case of R, here total boundedness and continuity enough guaranteeing the compactness of T. But in other cases, it is not true. You have to add some more conditions. So procedure is same. This is same procedure. Now operator, this equation is converted into operator equation. Up to this, it is all right. Now you show that T is continuous and completely continuous. It shows that it is completely continuous. Completely continuous means continuous plus totally pre-compact or totally boundedness. You have to prove. So for this, you have to make use of the Arzelà-Ascoli theorem in Banach spaces. Sometimes if Banach spaces is not real one, then you have to apply that Kolmogorov condition for the compactness. So different. So and for continuity, you have to show dominated convergence theorem. There are so many analysis you have to use here, make use of here. You have to use so many analyses. Making use of those results from analysis, you can prove this operator is continuous as well as completely that totally bounded means completely continuous. If and you have to consider one say close continuous and bounded subset of that Banach space. It is very simple to consider that. So if you consider like the wall, so this is the integral equation. This is the integral equation. Very simple. This is the equivalent integration to this. Now we consider the ball centered at x0. We consider this ball. And so here R satisfies certain conditions, constant. Simple, very simple. So like let us find that R here. So what is the here x of t minus x0? It is equal to mod integral e0 to t mod f is less than equal to, yes, like this. Okay, like this. And this is bounded em and here. So it means what? So this is the ball EMA. This bounded limit of integration from t0 to t0 plus 1. So EMA is a bound M is a bound. M is the bound of this nonlinear function. So EMA. So we consider open ball centered at x0 of radius r. This is r. It is closed, convex, bounded. Every ball, I mean closed ball, is always closed, convex, and bounded. And so show that this operator maps this ball into itself. It is easy to do. It's very easy. And once we show it maps a closed, convex, bounded subset into itself. Again, you just if you prove that it is continuous and complete and totally bounded, by application of this sort of fixed-point theorem, we get the solution. See here, this is the only Varna quantization principle is the only theorem or its generalization in analysis which gives both existence as well as uniqueness. Short of fixed sum does not give uniqueness, it only gives existence. It has a solution, that's all. Even both the fixed point theorems, from this we don't confirm infer that this is a solution. This does not provide a solution. Varna quantization principle also does not give the solution. It just approximates the solution, because infinity we don't go up to the infinity. It approximates the solution, and this is the existence. That much we can prove with the help of both this. Solution we never get, because for nonlinear differential equation we don't get the solution. It is like this. Suppose another here we don't get, we do not get the Lipschitz condition. Lipschitz only compactness condition is enough. Suppose function is not Lipschitz, again is not even continuous. Then the problem has a solution. Again problem. Does this problem have a solution? Function does not satisfy Lipschitz condition. Function is not continuous, not bounded even. Does this problem have a solution or not? This is again problem. So then there is another fixed point theorem, Tarski, discrete fixed point theorem. So it doesn't give any continuity, any compactness, any Lipschitz condition. But in that case, so the space under consideration, in which you are placing the problem, this should be complete lattice. This is problem, it's a big problem, because this space that CJR is not a complete lattice. Many spaces they do not possess this property. Partial, if you introduce a partial order, doesn't always it becomes a lattice. So this is a problem, big problem. But it is lattice. Then you put here condition that this is monotone on x, monotone non-decreasing in the second variable x. It is more, and procedure is same procedure up to this. So for every application, procedure is common up to this. Up to it is common. Here you just apply that monotonicity of the f, non-linearity of nonlinear function, to show that this operator is monotone isolated increasing or monotone non-decreasing, like that. Space is complete, that complete lattice. It has a fixed point. Not only fixed point, it has a maximal fixed point, minimal fixed point. Means it has a minimal solution as well as maximal solution. So additional information you will get. So this is tight position, but additional information you will get that the given differential equation has a minimal solution, as well as this is the additional information you will get from that Tarski fixed point theorem. So this is about your, these are the basic fixed point theorems, fundamental three fixed point theorems of the nonlinear analysis. So two are given by, I think, the Polish mathematician Schroeder and Banach. I think Tarski from USA. He might be knowing Tarski.
risky
question. I have no idea, but he's third fellow from I think USA, maybe USA. Maybe. So they are the famous fundamental theorems of the nonlinear analysis. Application like this, right? So my problem now, suppose function is not continuous, does not satisfy Lipschitz condition, and not monotone. But what can be done? Problem is, does this problem have solution or not? Does this problem have a solution or not? Yes, even then, problem has a solution. But it is just tricky thing. Procedure is same. Procedure is same. Just I explain here. Let me see here whether it is written here something. Oh, is it okay? Yeah. So what is hybrid differential? My problem, my talk is on hybrid differential equation. No? So I have to catch that point. So what is a hybrid differential equation? You know differential equation. You know nonlinear differential equation. Suppose then in case of unaccompanied control principle, F satisfies geometric property, linear, analytic property, Lipschitz condition. Lipschitz condition is metric property. In case of that Schroeder-Fishbane theorem, it satisfies compactness property, compactness condition, which is topological property. And the algebraic property, in case of Tarski-Fishbane theorem, there is one algebraic isotone property. We need these three properties for different Fishbane theorem. But if F does not possess any property, not Lipschitz, neither continuous nor that we can say monotone, then what can be done? Does this problem has? It is a problem, and this problem has been settled by that Russian mathematician M.A. Kaspersky. So suppose this is the equation. How to explain the technical criteria, technicalities of this theorem? So this is the problem. I think okay. This is the differential equation. So selection of Fishbane theorem depends upon the situation, circumstances. Remember, in every case we cannot apply all the Fishbane theorem. See the circumstances, see the nature of the nonlinear function involved in the differential equation, and depending on that nature of the differential equation, you can consider which Fishbane theorem can be applied. So I already told you, good collection of Fishbane theorem give you better results. Not only this existence, uniqueness, apart from that, you can discuss other qualitative properties of the differential equation, like the stability of differential equation, attractivity of differential equation, attractivity of two solutions, monotonicity, positivity. So many qualitative properties we can discuss with the help of this Fishbane theorem. I also applied all these Fishbane theorems in my work. You can go to Google and find my work. So this is the problem. Now F does not satisfy Lipschitz condition, neither nothing like that. What he did, Kaspersky did, so he splitted this function into two components, like this. He splitted this function into two components, like this, in this form. Two components. First component, he split it like this. This is the addition of two components, split it into two components. And where this nonlinear function, first component satisfies Lipschitz condition, second condition satisfies the compactness condition, and then this may have a solution. He proposed and he proved one theorem. That is a I consider it to be a habit. First of all, I explain what is differential equation. So if this nonlinear function, this is only one, there may be 2, 3, and so on, no problem. If this nonlinear function or nonlinear functions involved in the differential equation, nonlinear differential equation, possess mixed properties from different branches of mathematics, mixed property, hybrid, that is hybrid, from analysis, algebra, and topology, like this, mixed properties. Then we say it is a hybrid differential equation. Now, this becomes If we split this into this, here F1 satisfies Leibniz condition, this satisfies compactness condition, then inversion, then it becomes a hybrid differential equation. See, this which one? This differential is not hybrid differential equation, this is hybrid differential equation. So this is a hybrid, it becomes a hybrid differential equation. Because, so this is a differential equation. This is split into two, subject to same initial condition.
You can use differential. Differential. This job is better.
Okay.
This is harder.
Okay.
That is a hard. Another one is soft.
So inversion. So this is the differential equation, hybrid differential equation. So what happens? See, now we'll talk this. What happens here? If you invert this, the inversion of this differential equation gives you sum of two operators like this. F1, F2. So inversion of this differential equation gives rise to this integral equation. Integral equation is the sum of two. You may consider this one operator, and you may consider this to be a second operator. These are two operators. Remember, and he formulated that M.A. Such Cartesian mathematics formulated a fixed point theorem involving the sum of two operators like this. So what is the operator? His operator equation. So we consider this equation. This is the second equation from the hybrid fixed point theory. Second equation. First equation, that one. This is the second equation from hybrid fixed point theory. So he proved a fixed point theorem for this sum of two operators. A is contraction, maybe nonlinear contraction. First of all, he proved only for linear contraction, only contraction. B is completely continuous, compact and continuous, that is completely continuous. Then this operator has a solution. He proved like this. His statement is like this here. In a closed subspace, of course. It's not here, no? Okay.
So, such type differential equations have applications?
Yeah. Number of applications. Usually, so many authors, you read the literature. Of course, whatever I explain here, definitely it has application. So you have to find the physical situation. Physical situation, you find the physical situation. Oh, this is what is the year of this? 1964. Since then, people are working on this problem. Since then, people are working on this problem. Famous problem. Casimir fixed problem is famous. So remember here, there are four parts of nonlinear analysis. Pillar, you may say one building of nonlinear analysis. It is considered to be one building. Four pillars of this building are this analytic fixed point theory, topological fixed point theory, algebraic fixed point theory, and this hybrid fixed point theory. There are four pillars of this building of nonlinear analysis, and both are all are the famous, commonly used here. In 1964, Krasnodar proved this theorem. So its statement is nice. I reproduce here. Let S be a closed, convex, and bounded subset of a Banach space. It is addition. It is not nonlinear space. So it is Banach space. Remember here, the theorem is Banach space. Banach proved in metric space. So order Banach, this is Banach space. So S be a closed, convex, and bounded subset of Banach space. And there are two operators. And let these two operators S from. So Banach space say X, we can say yes from S to X. So no, these two operators satisfy two conditions. Number one condition A is contraction. Second, B, one condition, A condition, B condition. B is completely continuous. And C, this condition must satisfy. Then the hybrid operator equation, it is a hybrid operator equation because two operators satisfy different properties for different branches of mathematics. Operator equation Ax plus Bx is equal to Ax. So this has a solution. This has a, this is a famous Krasnodar Fixed-point theorem, proved in 1964. This is 1964. So I just take a few words about this fixed-point theorem. Then I will come to that application. So this is the original fixed-point theorem proved by Krasnodar. Yeah.
Both operator from the S to
Yes
X.
to yes, yes to X.
And,
Original
but
fixed-point theorem.
you put here C condition AX plus BY. Why not the same point like A plus B of X?
No, B is what? AX plus BY.
So
X and Y belongs to S.
but maybe it may be something sum of the two operator A plus B of X. Why not like sum of the two operator condition?
Huh.
But you are
Different,
trying
but
to use a different point.
but this is the condition. Maybe outside that set, but this is the condition of that theorem.
he want to say that bx हो जाए तो क्या हो bx होना चाहिए
So BX is
No, 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 no. For different position,
but
it is special. It is
then of course
it is a special case.
special case.
Even it's two different operators, special case. So this is not the, AX plus BX. Don't consider for different point also.
Question is that when we define a sum of the two operators,
Uh-huh.
we define like A
AX.
plus B of X.
Yeah.
So that is something A.
Here like this.
Yeah, that's the
Here,
fixed point.
but this is the condition he has put. AX plus BY for all points X and Y. Addition should be in yes. This is the condition. Later, after some time, Theodore Burton from USA, he improved this condition. Then myself also, improved this theorem a lot. So what I did instead of this, so A and B are, what is this? A and B are from S to X. So A may be some other M to X, B may be from S to X. It may happen. But in this case, we have to show M is equal to S. This should be, but this is not always the case. This is not case always. So I just extended this restriction. I extended like this. A is from X to X, and B is from S to X. It is like this. And I weaken this condition. This strong, very strong condition. I weaken this condition like this. So X, if X is equal to AX plus BY, implies X belongs to S for all Y belongs to. So I have weakened that condition. This is a strong condition, and this is applicable everywhere. That theorem is not applicable everywhere, but this is applicable everywhere. So I weaken this one. This is extended. This domain is extended, but this condition is restricted. This condition. So this has so many applications. This particular. So here linear contation. This contation linear contation. Here I just replace it by nonlinear decontation. Again, so many applications. So I have improved A as well as C, and here extended this like this. So this is a famous theorem. So many applications. In my papers, you will find a piece of this. So I proceed as here. If there is a differential equation of this kind, so differentiation X dash of t is equal to sum of two operators, sum of two non-linear differential equation. Subject to some initial condition. So whole discussion can be applied to boundary value problems also. This is for the sake of convenience for you and myself. I just IFPs. I use this IFPs, initial value problem. So with initial condition like this. So this is the differential equation. So it is a what is kind of this equation? So actually original equation is that one, A dash U2 F Tx, right? So I have perturbed it, I have splitted it. This is one kind of perturbation. It is called perturbation of linear perturbation of first kind. So all type of perturbation I have given one paper. I have discussed all type of perturbations, modification of this problem. So paper appeared in differential equation applications. So you can see under that Google, you will get that paper. So like this, it is a perturbed differential equation. Perturb, they are original. What is the use of perturbation? You know, if you want to wash some clothes, right? Then you put some soap, something, and then again stir it well. Something. If you add something, you subtract something, you get the solution. Whatever you have, to make the cloth clean. So it is like that. So you add, function is added. Like this. It is splitted out just into two like this, two functions, written like this. So now procedure is same. You convert into equivalent equation. by using the theory of calculus. Using the theory of calculus, that you will have to use that fundamental theory of calculus. Same procedure, everything is same. You first find the appropriate function space. If this is here for all t belongs to j, if you write like this now, then solution will be where? Yes. If you put like this is true for almost every t belongs to j. Substitute integration. Where the solution will be? Where the solution lies? You know? Simple. If it is not there, you can consider you can place this problem into CGR. But if this is almost everywhere, you cannot place this problem. Solution does not belong to that space. It belongs to this space. Space of absolute continuous real value function on closed element of j. It is solution belongs to this. So you have to see where the solution lies. Problem is given. You have to see where the solution lies, and you select appropriate function space, and you place your problem into that, embedded into that function space by selecting some norm. It becomes a one-arc space. Then you just choose this to be 1. So it is equivalent to this one. You choose this operator A, this operator B. This satisfies Lipschitz condition, this compactness condition. This is contraction, this is the completely continuous, their operator. And you will have to one more condition, you have to set this condition, this condition. Take the norm on both sides. This is bounded, this is bounded. So all conditions are satisfied. Hence you can apply this fixed point theorem. It is a hybrid fixed point theorem from sum of two operators. The first hybrid fixed point theorem among these two is first in this form. So we got the solution. And solution of this is the solution of integral equation. And solution of integral equation is the same as solution of this differential. Proof is finished. A little skill, some computation, nothing else. But you should have some knowledge of the analysis, calculus, all these things, some topology. Topology is very important. Topology. Unless you have topology, the convergence and compactness, how will you understand? You need all the knowledge of all three branches. Then and then we can apply here hybrid fixed point theory. Otherwise, you cannot apply. You first study analytic fixed point theory, topological fixed point theory, that is the algebraic fixed point theory. Then and then only you can go to this hybrid fixed point theory. And hybrid fixed point theory has number of applications. Number of applications, you can prove all other qualitative properties of the solution, stability, asymptotic stability, there are so many definitions of stability, attractive of solutions, positive solution, whether solution is monotone or not. So many things you can study, discuss. So this is the first hybrid fixed point theory. So local solution also you can prove here, like local solution. So next, second, another. Still people are working this, modifying this condition like this. So another basic fixed point theorem is, it is similar to this, a little different. This is sum of two operators, that is the product of two operators. This is the fixed point theorem correspond to sum of two operators, and that is the product of two operators. Same, but product means we have to discuss in algebra, Banach. We have to go into Banach algebra. In Banach space, you won't get a product like this, right? You have to go into Banach algebra. So theorem is put in Banach algebra. So like this, let S be a closed continuous bounded subset Banach algebra X. X is a Banach algebra. This closed continuous bounded. This is Banach algebra. So what is Banach algebra? You know. So product is well defined, and this norm of this product is less than or equal to norm X into. So it becomes a Banach algebra. So second hybrid fixed point theorem. This is also famous. Many people apply this. Even Professor Lakshmi also applied this one for your information. So same, not much difference. So previously it was like this. This is paper is put in Journal of Mathematical Physical Sciences, 1997. Say almost seven, something like that. Long back, when I was started work, I worked on this problem in the beginning. So this theorem is proved. So S is a closed continuous and bounded subset of a Banach algebra X, and yes, two operators are from S to X, like this. A is not contraction here; it is Lipschitz. with Lipschitz constant L, whatever it may be, L or alpha, you may say. Lipschitz constant. It is Lipschitz, not contraction. It is Lipschitz. Second, B is completely continuous, no problem. Third one is, it is completely continuous on S, so bond exists. We write next. So third one is like this: Ax By belongs to S, or all xy belongs to it, like this. And fourth one, there is one more condition. Here alpha m is less than 1, where what is the m bond of it exists, supreme of this x belongs to it exists because it is complete, it exists, compact, it exists, the supreme exists. So if these four conditions are satisfied, then operator equation has a solution. Of course, solution is yes, of course, it goes yes. So this is the second fixed point theorems. I have proved in 1997, like this. Have so many applications. I applied in the beginning. I applied to nonlinear integral equation, quadratic integral equation, product of two nonlinearities, integral equation. Then applied to nonlinear differential equation also. I worked with Donald and Reagan. So here he applied Donald Reagan. So here we applied these fixed point differential equations under suitable conditions. So next, I again improve this. Later I improve this. Lipschitz to this, only phi Lipschitz with d Lipschitz. General with d function, I generalize it, improve it, psi, like this. B is completely continuous, and this instead of this. So x, if x equal to ax plus by, implies x belongs to S for all y belongs to S. Of course, this condition is also there. Here condition is modified. So m into for r positive. M is like this. M is equal to norm like this. Second fundamental hybrid fixed point theorem in the analysis, nonlinear function analysis, nonlinear analysis. So I have improved first condition from Lipschitz to d Lipschitz, generalized, improved. Then this condition is improved. Improved means what here? That domain is extended here like this. B is from S to I. It is like this. Domain is extended. Once domain is extended, we can restrict, you can improve this condition as well as this condition. So first condition is about that d Lipschitz. Second is complete continuity. So this is the somewhat improved condition like this. And this is the opposite you should satisfy. Under these four conditions, this equation is improvement of previous theorem. Lot of applications, number of applications. It has a solution. So this can be applied for differential equation like this. So this is a hybrid differential equation. I have considered myself Donald Reagan. So initially myself I have investigated this particular differential. Yes.
We are talking ax into bx is a product.
Product.
Operator.
Yeah, operator. It is one element of this Banach algebra. Ax is one element, bx element, another element. Banach algebra. Yeah. So Donald Reagan myself applied this fixed point theorem to this equation. Subject to initial condition. initial value problem. So this is the quadratic differential equation. So this is the perturbation of the original differential equation. It is a perturbation of second kind. Quadratic perturbation of second kind means product like this. Quadratic second kind. So if you perturb right hand side, it will be perturbation of first kind. If you put left side, perturbation of second kind. It is quadratic. It is not linear. It is quadratic. If product, this is quadratic perturbation. Hey, this is quadratic perturbation of second kind. So this differential equation we have considered, and this paper is published in functional differential equation with Dolan-Regan. I think same paper, some modification of that is also published with that R.P. Agrawal, Dolan-Regan and myself in some papers like this. So many papers are there on the problem. So procedure is same. Here remember, instead of Banach space, here it used to be Banach algebra. Remember Banach algebra. So you define suitable norm, right? You find first of all you find what do I do my solution of the differential equation. Where solution lies. First of all you have to see the space where the solution lies. And then you can decide the space in which this problem should be put or placed like this. Find this particular space. If you place this problem in the particular space, then find the equivalent integral equation, that is usual theory. Using the theory of calculus, you convert this equation into integral equation like this. Procedure is same. Procedure is same, huh? Plus same. Like this is the equivalent integral equation. This operator is A, this operator is B, and show that these two operators satisfy all the conditions of this hybrid-Fishman theorem. Second fundamental theorem, hybrid-Fishman theorem in the analysis. If these two satisfy all these conditions, then this equation has a solution, integral equation, implies and implied by, so it is a solution of this differential, hybrid differential equation. Procedure is same, very simple. It's not difficult how to apply Fishman theorem and so on. You should have knowledge of calculus thoroughly. Your fractional differential equation, you should have knowledge of fractional calculus and so on. So this is about your two fundamental. What time left? I have not touched my topic. I am interested. We are the builders of hybrid Fishman theory. So this theory is initiated in India. It is India's contribution. Remember, in Fishman nonlinear analysis, this is India's contribution. There are so many hybrid Fishman theorems from our country proved, you can say, produced. So I am interested in hybrid Fishman theory, but time is limited. I can't go to that my topic. Although that particular recent latest Fishman theory, this is old one, latest, very interesting. See, just I will quote one or two sentences about that. Yeah. So if the function f is not, say what you can say, Lipschitz, continuous, your algebraic like this, then so there are another type of hybrid Fishman theorems. So this is the topo-hybrid. These two theorems are topo-analytic, means a combination of two arguments from one analysis and one topology, two arguments. So there are Fishman theorems from one argument from lattice theory, one argument from analysis. Similarly, another one argument from topology, one argument from, and there are four types of hybrid Fishman theorem. So we combine all these three, one argument from analysis, topology, and lattice theory. Very interesting Fishman theorems. Number of applications. So if you are in doubt, you can ask me now and afterwards also. No problem. So time is limited. I am very much thankful to Javier again. So I have a chance to exchange my ideas with Professor Khamsi and all you people. We got inspiration from young people because we expect something from young people. So you follow this line, and I say one problem, simple problem, open problem for you all. So we are in Banach space. Yes is the normative closed canonical subset of Banach space X. You consider this operator equation. You consider three operators, Ax plus Bx plus Cx. ABC are operators, and find the condition, appropriate condition on A, B, and C, so that this operator equation will have this open problem to you all. Thank you very much for, again I thank Professor Ali Javed, he is my good friend, for giving me an opportunity to speak here.
Thank you very much. much, Professor Dagi sir. We are still learning from you, and he's no doubt he is very nice work in this area.